Um, let me first apologize for the lecture last week that I cancelled. It was, last minute change in the agenda of the school for an important meeting, and I couldn't come for the lecture. We will have the Easter break now, and then we will continue with the semester until the break for the mid-semester break. And let me just mention I mentioned you that if you want to prepare and volunteer for the topics that I propose you for kind of additional work where you can study yourself and find material and then present stuff. For the moment, we have only the part on audio, voice coding. The first opportunity will be Tuesday, not next week, the week after next. Okay, so we will have a 2 hours lecture plus 1 hour, depending 1+ hour, for those of you that volunteer for presenting this part. So the rules, I will put a note on the web page, but the rules are the following. This is something that replaces the additional topic at the exam, right? So at the exam we have the opportunity for those students that want to, during the written exam, propose me some specific topic that was not covered during the lectures, and this is for 2 extra points, right? If you volunteer for giving a presentation in front of your colleagues, this is equivalent to the additional topic, but the value is 3 points instead of 2. Okay, that's the difference, right? The presentation must be either with slides or on the board, on the blackboard, and the assumption is that you have to prepare material for half an hour. Okay, so that's the rule. Okay, and of course I perfectly know, right, that it's not easy. It's a lot of additional work for you, but it can be an interesting experience, right? It's part of the soft skills that you are expected to acquire during your master, and that's one opportunity that you have, right? Receiving, it's not only presenting, but receiving feedback from me and from your colleagues. The other topic that I will not cover for sure will be radio planning. Okay, you already have the material on the web page. I will say you something when I will get there after some of next lectures. And in that case, my suggestion is that this is covered. This can be an interesting topic for those of you that already attended the course of Fundamental Operation Research and possibly also graph theory. Okay, so for those, how many of you attended Fundamentals of Operation Research already? Okay, thanks. How many graph optimization, graph theory? No, nobody? Because you have it in this next semester. I see. Okay, good. So of course, those that didn't attend at all the course of Fundamental Operation Research, in that case, it's tough to prepare the lecture on radio planning, right? But in order to at least follow what your colleagues will present, on the web page there is a set of slides that is kind of a really concise overview of the basic topics of optimization and in particular discrete optimization. Yes.
The password of that files is the number of the tools, but it's changing, so we don't have the password.
You don't have the password for the slides of the optimization?
Yes.
I didn't remember there was a password.
The code of the Morse code.
Okay.
But it's changed and
Okay. I will try to find the old code number and give you the password. Or possibly I will replace the file with a file without the password.
I have this number.
You have the number? Okay, correct. Then you were right on the board, okay? Very good.
For the slide? But not the new slides.
Now for that part,
No, you remind slides.
so you have the slides on the basics of optimization and discrete optimization in particular. You have my slides, but you cannot use those slides for your presentation, of course. And you have a book chapter. There is a book chapter in the list of suggested readings. That is the one that you can consider, right? This is the minimum, of course. If you find yourself some additional material that can be used for this purpose, of course, this is considered a plus, right? So that's the rule. Similar thing for the other topic, okay? And also, I can also tell you that we will have toward the end, we will have a former student that is now working in Ericsson. He's very active and expert of 5G, and he will give us a seminar, 3-hour seminar on 5G towards the end of the course. Okay, very well. So let's continue then with what we are doing. We are doing now. So we discussed of the capacity of CDMA. I mentioned power control already, and now the point is understanding how we can define the capacity in terms of how can a cell know in advance where to stop in accepting new connections, new calls, and new data sessions, right? So this is what we typically call admission control, right? This is another interesting general topic, which is more general than it may appear here, right? Because we are used to the concept of capacity, and typically when we say capacity, and this is what we will continue, to use in this course, when we say capacity, basically we assume that we have a fixed amount of resources. We know how many resources are consumed by each request, and simply we stop when we don't have enough, right? That's the obvious way of limiting the new calls and new requests when they come if you don't have enough resources, right? This is not always the case in general, in particular for two reasons. The first reason is you may have connections that don't require a precise amount of resources. You know the characteristics of the connection, but this is not a fixed amount of resources. It can be variable. Think, for example, to data connections where you don't have a fixed rate, like in the case of voice calls. If you don't have a fixed rate, then can you say it fits or not in the available capacity, residual capacity? Well, the answer may be yes, maybe not, depending on the rate that this connection will use. If you don't know exactly, if you have limited information on the connection rate, then of course your decision may be based on other criteria. This is first reason, and this is one of the reasons why limiting traffic in general in data networks with variable rate traffic is not that trivial as it may appear. Okay, so that's the reason why the problem is general. In our case, there's a difference. Of course, you may have variable rate data connections, right? But in the case of CDMA, you also have variable capacity. So the capacity is not fixed, okay? How can you say if a new call can fit or not the capacity of a given cell? The problem is that we know that a cell has a capacity which depends on a constraint on the signal to interference and noise ratio. If the signal to interference and noise ratio is above a threshold, then after we include the new request, the new call, then it can be accepted. If we cannot meet this constraint, then it cannot be accepted, right? The point is that interference is variable, the rate is variable, the interference is variable, and as a result of this, you may have a capacity which is not precisely defined, like we did with the approximated formulas that we used so far. In particular, if we consider the case of power control that I described to you last time, in the case of power control with closed loop, the case where you set the target signal to noise ratio or a BO and zero value, then you have kind of a control system that is able to keep the system at the equilibrium point. All connections have the same signal to interference and noise ratio to the receiver, and you adjust powers in a way that this condition can be met, right? And we discussed last time that this is equivalent to a system of linear equations with n variables and n equations, where the n variables are the power emitted by each transmitter, right? That was the problem, right? Now, in CDMA, typically, again, there is a large literature on this for those of you that are interested in this topic. We say that capacity is not hard defined, but it's a soft capacity. Soft, again, is exactly the concept that I just explained. So we don't have a fixed definition of capacity, clear definition of capacity. The capacity depends on the interference, so can be variable over time, so it's soft. But it's soft also in the way we decide, accept or reject a new call, because it depends if we can figure out if the new call can fit or not the capacity. Okay? So ideally, what we should do is the following. Follow me. You have the equations, linear equations for power control, right? You have n active connections in the system. You had 1, so instead of n plus 1. Can it fit or not? That's the decision, right? Ideally, what we should do, okay, is the following. Let's try to see if with n plus 1 connections, n plus 1 variables and n plus 1 equations, we can find another equilibrium point. If there is another equilibrium point, then we can accept the new call. If we cannot find another equilibrium point, either because we don't have enough power or because the solution of the system doesn't exist, in either case, we should reject the call. Okay? That would be the ideal situation that we have. Okay? How can we do that? Well, that's something that is more complicated than at the moment irrelevant. There are, in principle, practical mechanisms that you can use. But let's try to, let's assume that we can do that. We can take the decision after we make the check on the equilibrium point of the power control. So if the equilibrium point exists, then we accept the call. If it doesn't exist or it's unfeasible, we don't accept the call. We reject the call. What I want to point out here is the following. The decision in this case depends on the call that is, on the request that is arriving to the system. Okay? You can easily figure out that if we have a call that has good channel conditions, for example, a user which is close to the base station, right? Then this one will generate little interference because can use a little power. And typically, in that case, we have more chances to accept the new call because the perturbation that we had to the system is small. If we have a request coming from the user which is far away from the cell, at the cell border somehow, of course, the power requested to get the target signal-to-noise ratio at the receiver will be higher. The interference generated will be higher. So the probability that with the new call we don't have another equilibrium point is higher. Okay? So the decision, yes or no, accept or reject, actually is not depending only on the system, but also on the request. Okay? So we have a system that, in that case, becomes selective depending on the channel conditions and interference situation. This phenomenon is known as cell breathing effect. Breathing, right? Why? It's easy. If the load is low, of course we accept all requests because we have enough capacity, regardless if they are coming from users that are close or far away. While we get to the capacity limit, we have a smaller spare capacity, and in that case, since the capacity is small, which is, again, the capacity is a margin on the maximum level of interference in the end in these systems, we can accept only new calls that generate little interference, which means that we can accept calls also only from terminals that are close to the base station. So when the cell is lightly loaded, it's big. When the cell is heavily loaded, it starts accepting traffic only from those terminals that are close to the base station. So it's kind of the size of the cell by itself is not fixed. It starts moving up and down, right? And that's, of course, something that is not necessarily a good thing, because in principle, in CDMA systems, if you adopt this kind of approach, what will happen is that if you have, for example, a given moment in time, a big event somewhere in the city with a low and very high traffic, well, probably what you will see is that the cell radius will start reducing, and the system will start accepting only calls that are close to the base stations, and this can even generate holes in the coverage. Okay? This is one of the reasons why managing CDMA systems is not particularly easy. Okay? So this is also the reason why in practice you don't do such complicated things, but you use a logic which is, this is what I exactly said you, the ideal one. What you do is something that is much simpler. You typically make decisions based on either an hard limit, like we did in the case of the simplified formulas. So we calculate an Nmax, and this Nmax is calculated under assumptions that make all requests equivalent, so you don't consider that some of the requests generate little or much interference, but you just calculate the total number and then you take a decision. This is first approach. The second approach is you just measure the level of interference and you take decisions based on a threshold. Okay, so you generate the receiving power, which is kind of the, the background noise. If the background noise is too high, then you stop accepting new calls. and as you can understand, in both cases, you don't discriminate between different requests. It's only, the decision is only based on the status of the system, not on the type of request that you get. Okay? Clear? Clear for everybody? The second one is the one based on the level of interference, also known as noise margin. Why noise margin? You can find this name in the books or in technical papers, because typically you don't consider the absolute value of the interference level. You typically consider the interference level with respect to the background noise. Okay, that's the reason why we have this concept of noise margin, right? It's how much interference is compared to noise, background noise. Okay? But that's this based on this threshold is the most common. Okay, so in CDMA systems that we use every day, the approach is based on just a threshold on the interference level, which means that the capacity is really adapted to the real conditions, right? But it's not generating any self-breaking effect. Now, for us, okay, this is somehow important, and I said is connected to the concept of power control, and the reason why we have this, capacity, soft capacity in CDMA systems that is depending on the interference levels, right? However, we still have an open point that we didn't cover yet, which is related to the definition of capacity in CDMA systems in case we have different classes of traffic, like in the case of TDMA that we already discussed. Can we have something similar to the extended Erlang B formula in the case we have multiple rate transmissions in CDMA? What's the difference? How can we extend the concept of capacity, approximate formulas for capacity that we already obtained for CDMA, right? The first question for you is the following. So we know how CDMA works. The point is, before understanding how we can extend the concept of capacity in the case of multiple rate connections, how can we have channels, sub-channels in CDMA with different rates? Clear for everybody? So we have, in TDMA we already know, right? We just have a different number of time slots per frame, and that's the way you have different rates per sub-channel. How can we achieve the same with CDMA? Any suggestion? Yes? Different codes? The codes of different channels are different by definition. What do you mean?
Code rates.
Code rate. Different code rates. Do you agree?
Yes.
Good. Why? That's important to know, right? Because let's try, right? Let's try. So you have information bit, right? And then you have the code rate, which is the rate of the code that you. So the number of bits per symbol is our spreading factor, right? Clear? So you agree that the chip duration is, of course, related to the available bandwidth that you have for the system, right? Right? And this is fixed. It's given, right? Which means that given the spectrum availability for the system, this duration of course, depending on the specific waveform that you use, is fixed. Okay? So if, for example, instead of using a code like this, you use a code which is half length here. So we divide it by 2, and we use a code length which is half the previous one. Okay? We are not changing this duration. This is fixed. So what are we really changing? We are changing the duration of the symbol, right? So we are halving the duration of the symbol, which means that we are doubling the rate. Okay? So simply, the information rate is inversely proportional to the spreading factor. If we want to double the rate, we halve the spreading factor, right? Simply. Okay? So how can we get channels with different rates? We just use codes of different length. Simple. Clear? Simple, right? Very well. Now we have clear doubts, questions. So now, what we have done for the approximate formulas for CDMA capacity is the following. We have calculated a value which is Nmax, and in particular we have calculated it as 1 plus 1 over B, where B is a constant value, which is the ratio between the value of the threshold for a B over N0 divided by GP. Right? This is our constant value that we use for the definition of capacity. Right? This is exactly the formula that we calculated, right? And this is, for example, the simplified formula for the single cell, but we have something similar also for all the other cases that we have analyzed, right? So in any case, we have something like this, right? We have a constant value, right? Now, let's try to understand if we can extend this calculation also for the case where you have not just one traffic type, but you have multiple traffic types. So, of course, the only relevant part that is affected by the information rate is, of course, GP, right? GP is given by the bandwidth divided by the rate, the information rate, right? So, if we have different information rates, we have different processing gains. So let's assume that we have a set, exactly like for the case of the extended airline formula. Let's assume that we have a set of different rates, R1, R2, Rn. So M traffic classes. Okay? Clear? Even more than that, let's assume that we have a basic rate R, and that all the other rates are integer multiples of this basic rate. So D1, D2, Dm are integers, and R1 is an integer multiple of the basic rate R. Okay? So basically, given R, given this basic rate, this kind of minimum common rate, all the rates that are used in the system are defined as multiples of this one. Okay? And these factors, integer factors, D1, D2, D3, are known. Okay? Now, easy. So basically, in the structure of in all models that we have seen, including the one for the single cell, what we have done is basically setting the signal-to-noise ratio, signal-to-noise and interference ratio, greater or equal than T, which is a threshold, constant threshold, right? Which include the GP, whatever, right? Now, you can easily see that considering the specific expression that you have so it's So the power, P, is proportional to the threshold times the interference. But this threshold, the threshold that we have, is exactly given by the value that is defined according to the formula, right? So it's given by the threshold in terms of AV over N0 divided by GP, and GP is B divided by the rate. So this is exactly what we have written here, right? So it's the threshold, like here, the threshold divided by GP, the threshold divided by GP, which is B divided by the rate. Clear? Okay, times the interference, right? So if we assume the interference level is constant, so we are just analyzing the impact on the power for a specific connection. If we start modifying the rate of that connection, so if we just modify one connection and keep the other unchanged, right? We can easily see from here that the transmission power that we need, the power that we need, is proportional to this constant D. So if we double the rate, we have to double the power. Clear? Which is, if you think about that, perfectly in line with the assumption that in CDMA everything is, the concept of capacity is somehow related to the interference generated, right? And actually all relations are in the end linear. If you want to transmit at a higher rate, you have to linearly increase the power, okay? And also, of course, the interference you generate. That's in the end, you know. And everything is, again, very obvious if you consider CDMA, not only because of, you know, the spreading process and the processing gain, but simply because it's regulated only by the equations on the signal to interference and noise equation. Okay? That's it. So, if this is true, then we can write the capacity equation considering the interference at the denominator to be generated by a set of heterogeneous connections with different rates directly. Why? Because basically at the denominator we have the interference generated by the other connections, right? Now, instead of using for all the same power P, we use a power which is proportional to the constant D. So if we have a call of type J, the interference generated by the transmitter is DJP and not P, like in the case they all have the same rate R. Clear? So now, then, at the denominator we have to sum all the interference, and the notation here is the following. Dj is exactly the constant that we have defined. Nj is the number of calls of type J, which is exactly the same notation that we have used for the case of the extended airline before. Right? So, let's assume that at the denominator here we sum everything. Okay? Let's assume that at the denominator we sum everything. Right? So then, of course, we have to consider that one of these connections, in particular, for example, a kind of reference connection which is at rate R, the basic rate, is at the numerator. Okay? So if we assume P is the power that you need in case the rate is R, then at the numerator we use P, and of course we have to consider the total power here minus P, and that's the interference. Right? Total power minus signal, that's interference. Clear for everybody? Perfect. and this must be greater or equal B, right? So if we solve this equation, which is exactly the same equation that we have used for calculating the capacity, what we get is the following. Sum over J of Nj dj must be less or equal 1 plus 1 over B. We know this is exactly the formula of the capacity. This is the capacity that we have defined. Capacity, Nmax, right? So we call it capacity. Capacity, right? And the equation then is sum of over J of Nj dj less or equal C, which is exactly the same constraint that we have used for defining the extended Erlang-B formula. So, if all the other assumptions for the model of the extended Erlang-B formula holds, all of them, then, which means Markov chain process, so which means Boston arrivals, call durations that have exponentially distributed, and so on. So if everything is in line with what we have assumed for the extended Erlang formula, then we can use the same formula also for the case of CDMA with multiple data rates. Clear for everybody? Of course, to do that, we need some specific parameters. So what are the parameters? The parameters are C, so we need to calculate the capacity. How can we calculate the capacity? So how is it defined? The capacity, as you can see from this formula, is the same capacity that we have defined before for CDMA. One of those that we have defined, single cell, multiple cells, discontinuous transmission, whatever you have. For which rate, so for which GP value, the GP value that you have to use is the one, exactly like in this case, corresponding to the rate R, which is the basic rate. Clear? The capacity must be calculated according to the basic rate R, this common rate that we use for the definition of capacity. Can be an existing rate for a service, for a classic, can correspond to a specific service, which means that, for example, we have a class D1, which is D1 equal 1. We really have this service with rate R. Or can be just a common rate, which is not used by anybody. Clear? Then, second set of parameters is the set of values dj. So these values dj are simply the ratio between the rate and the common rate that we use, small r. Simple, right? So if we have the capacity defined according to one of the CDMA simplified capacity formulas, and we have the values of the vector values dj for j, then we can directly use this model, the extended Erlang-B model, for CDMA systems. Clear for everybody? Clear? Questions? Questions? Now, so let me then make another step. So far we have considered connections and calculated the performance of the system with an arrival process of requests for these connections, and assuming that each request has a given rate. So the rate is known, as in given, right? As I was saying before, we also have the other important case where we don't know the rate. This is the service that we are considering is a data service, internet access, like we do every day with our smartphones. And instead of having calls, voice calls or video calls, we have, for other services with a fixed rate, we have data access, right? Of course, when you have data access, you know, apparently it's a completely different story in terms of what exactly you want to calculate for characterizing the performance of the system, right? And of course you have a large set of parameters that you may want to consider. But there is, however, one aspect that is today considered the most relevant one, and this is the one that all operators care a lot when they try to somehow evaluate the performance of their networks. If they want to, for example, analyze all the cells that they have and identify the cells that are critical in terms of capacity, this parameter that we will now try to characterize is the one that is considered the most important one. What is it? Let's first try to better understand what we mean with packet services and how we can characterize the behavior of the system in the case of packet services. Of course, you know, in the second part of the course, we will see how packet services are obtained with different technologies, from second generation to fifth generation. Okay? However, they have a common denominator, right? And this common denominator is dynamic sharing of capacity. We already mentioned it, right? So we have some physical layer technique for using the spectrum, and we obtain channels. Instead of using channels of fixed capacity like with circuit switching services, we use a single physical layer channel, and we share dynamically between all traffic flows this common channel. That's the approach that we use, right? Classical packet switching, right? How does it work in packet switching, right? Again, this is something that should be known from your background in networking. But you know that, for example, in wired networks like IP networks, you don't separate, of course, the capacity of network links between different flows. What you have is that you have arrivals at the nodes of the network, and then you have the output link, and depending on the arrival of packets that must be transmitted on the link, you have a queue, and you put the packets in the queue, and you transmit the packets that are in the queue one after the other over the output link. That's how it works, right? So managing the queue, transmission queue, is the only component that is fundamental for implementing this concept of statistical multiplexing that should be familiar for you, right? So we have packet arrivals, so we have routing, we identify the output link, and we just have an output queue. We put the packets in the queue, and then we transmit the packets one after the other. Okay? The packet can be as simple as a first in, first out, can be with some priority level, can be whatever you want. Okay? Well, usually in wireless networks, the approach is similar. Okay? The approach is similar. And we try to use the same concept of transmitting the packets one after the other over the link. However, we have to consider that the link in this case is a special one. It's an access link. It's the access capacity. So it's shared among the terminals that are transmitting to the base station and between the base station transmitting to the terminal, right? This is our spatial link, it's an access link. Okay? Can we do the same? Can we just use the same schemes that we have in this, that we are familiar with in wired networks, IP networks, for example, and manage the queue, transmission queue at the same, with the same approach? Well, more or less, we can do the same, right? In the downlink in particular, there is no problem at all, right? In the downlink, we have a single transmitter, so a single queue in principle. We can queue the packets and then transmit the packets in the downlink one after the other. That's, there is no difference in the downlink, right? In the uplink, of course, things are different. In the uplink, we have a mechanism for transmitting which actually need to define transmissions or schedule transmissions from different transmitters, right? So the packets that we transmit in the uplink come from different transmitters. Since these packets come from different transmitters, we need some help in managing the transmission queue. First of all, the transmission queue is not a physical queue because packets are physically in different transmitters. We need just to define the order of transmissions. So for example, first the red terminal, then two packets from the blue terminal, then one packet from the gold terminal, yellow terminal. It's gold, yellow, right? Okay? How can we define the order? Well, we need to know, in order to define the order of transmission, we need to know if the yellow, blue, and red terminals have packet transmit, yes or no, and how many, right? To do that, we need a separate signaling channel, which is a feedback channel, that is used for transmitting this information to the base station, so that the base station can tell, okay, now you transmit one packet, now you transmit two packets, now you transmit one packet, and so on. Transmission, uplink transmission scheduling can be done in a similar way to what we do in the downlink if we know how many packets are waiting in the local queue of each terminal. This approach, scheduling transmissions in the uplink, is the common one in mobile radio networks. You will see with Professor Redondi, of course, that you already know because you already covered some of the topics, that this is not necessarily the case in other technologies, like Wi-Fi, for example, right? In Wi-Fi, you don't use this approach. You don't schedule transmissions. You have a distributed mechanism for creating a coordination which is based on some random mechanism, right? In mobile radio networks, you don't do that. In mobile radio networks, you schedule transmissions in the uplink, okay? So, which means that before transmitting, you have to inform the base station that you have packets to transmit, and after you have informed, then it's the base station telling you when you can transmit. So we have scheduled ordered access. You don't have random access. You have ordered, scheduled access both in the downlink and in the uplink. This is the reason why mobile radio networks are considered, of course, more reliable. You can control more the way you access the channel, and the quality of the transmission somehow is controlled and guaranteed by the intelligence of the schedule, right? Then you can discuss if this is true or not, but in terms of technology, this is what we have, right? Okay? So of course, we will see how this is done. We will see how this is done in 2G systems with GPRS and age. We will see how this is done in 3G system with HSPA. We will see what is done in LTE and also somehow what is done in 5G, which actually is not much different from what is done in LTE. Okay? Clear? So the details, of course, are important, but the concept is the same in all systems. All. Okay? Clear? Now, the other difference that we have is in the transmissions. So you know that depending on how far is the user, how good is the channel that the user is using, the quality of the channel is different, right? And we know this because of the modeling that we studied of the channel, right? But we also know that if you have a fixed rate, like in the case of data connection, voice calls or video calls, you know that your voice will be correctly received if the transmission rate is constant. It's the one of the voice codec that you are using. Clear? Since you want to keep the transmission rate constant, what you do is that you can, and channel quality is varying, since you want to have a good quality in terms of bit error rate, for example, you use variable power. Okay? So power control that we have studied. So if your service is a fixed rate service, the strategy that is used is based on power control. If you have variable channel quality, but also your traffic doesn't have a fixed rate because it's data traffic, another approach, of course you can say, okay, I want to use the same approach, fixed channel rate, also for packets, for data, right? This is always possible, right? But an alternative approach is based on the concept of rate adaptation. What does it mean? It means that you have channel quality which varies, but instead of varying power, you keep power constant. Maximum power, for example. The power that you have, right? If the power is fixed, then, of course, the signal to interference and noise ratio of the receiver will be variable, of course, right? You are keeping the power constant, and channel is varying, interference is varying. What you get is a variable signal to interference and noise ratio, right? Now, of course, we know that either you have variable quality, which is not acceptable, because typically if you have variable signal to interference and noise ratio and you use just one modulation encoding scheme, you will have a bit error rate which will vary a lot. Let's assume that you want to keep the error rate under control, low enough, right? The target value for the bit error rate is a little bit different from the previous case, and the reason is related to the concept of capacity in case of memory channels that I mentioned some time ago, right? But that's another story. It's still a quality threshold, right? If instead of using one single modulation encoding scheme, you use multiple modulation encoding schemes, you can each modulation encoding scheme, depending on the scheme that you use, the modulation level, the code rate, will have a different curve for the bit error rate or block error rate, right? So if if you set your quality value, you can modify the modulation encoding scheme, picking the modulation encoding scheme which is the highest rate compatible with your constraint on the quality, bit error rate. Which means that instead of varying the power, you can vary the rate, information rate. So if the channel is good, you can transmit at a higher rate. If the channel is bad, you have to transmit at a lower rate. Well, the final result is rate, as I said to you, but actually to do that, you define a discrete set of modulation encoding schemes depending on the signal to interference and noise ratio that you have. So you estimate your signal to interference and noise ratio and you pick the rate corresponding to the value that you have, so that your rate will adapt to channel conditions, channel and interference conditions. This is something, again, which you already know. You know the formula of Shannon capacity, channel capacity, and you know that it depends on the signal to noise ratio, right? So the capacity depends on the signal to noise ratio. If you have a modulation encoding scheme which is good enough to approach the capacity, right? And you have not just one, but you have multiple modulation encoding schemes with different values of signal to noise ratio, what you can do is to follow somehow the log log scale capacity defined by the Shannon formula with your modulation encoding rate. This is what you can do. Of course, you cannot really have a continuous curve like in the case of the Shannon capacity. You need to have a discrete set of modulation encoding schemes and jump to one to the other depending on some channel estimation, right? So it's not continuous, it's discrete. And how many points, how many discrete values, this depends a lot on the system, on the technology. One of the characteristics of the modern mobile radio networks is that you have typically a very large set of modulation encoding schemes, which means that you can really follow very closely the capacity of the channel depending on the actual value of the signal to interference and noise ratio. Okay? Clear for everybody? Okay. So, power control for fixed rate connections, variable rate for packet access. Okay? Now, actually, so we have all the ingredients then, right? We have scheduling, we have channels with their rates. There is one more thing that is important to clarify here, which is the scheduling intelligence, right? And so I said to you that in packet networks like IP networks, you typically don't use sophisticated scheduling mechanism. For example, it's just a first in, first out queue. Not completely true. Probably if you have some knowledge of the management of elastic traffic, TCP traffic, you know that in the queues of IP routers, you use quite some intelligence in the definition of the scheduling policy, right? So you don't really send to transmission packets in the arrival order, right? You do some more sophisticated things, right? In wireless networks, you use some intelligence. And typically this intelligence is for ensuring that different traffic flows have some fair treatment by the system. How do you define different traffic flows? Traffic flows in mobile radio networks are very well defined because you have different terminals. So in the downlink you have traffic to different terminals, and in the uplink you have traffic from different terminals. You try to use some scheduling intelligence in order to fairly allocate the capacity available between different terminals, different users. Okay? So this is the approach that is used in wireless networks, and to some extent this is also used in other contexts, right? Even in IP networks in some cases, right? The problem, however, okay, fair scheduling is an approach which is typically very, very simple to implement. If you have, at a given moment in time, you have a given number of users that are active, I don't know, say n users, you try to fairly allocate the capacity between them. So if you have a capacity C, you try to divide this capacity by n and schedule transmission in such a way that you can achieve this average allocation, C over n. Okay, you do that, for example, in the downlink is very easy. Instead of using one single queue, you use multiple queues. And then you have a mechanism for selecting packets from the queue in such a way that you fairly allocate the capacity. So you simply calculate how many queues are non-empty. Of course, if you have empty queues, this is irrelevant, right? So n is not the number of terminals, n is the number of active connections, active flows. And you simply have a kind of round robin mechanism in order to pick one packet from each queue, right? Sequentially, right? It's not as simple like this, but somehow equivalent. Clear? Clear for everybody? This is the concept of fair scheduling. Okay? It's kind of a dynamic TDMA, more or less, right? But where you consider only the active flows. Same thing in the active. The difference, however, is that now these channels, these are different users. So when you then transmit to different users, these channels have different rates. Capacity is different in bit per second because they have different signal to noise, signal to interference and noise ratios, and according to the rate adaptation, you have in bit per second different capacities. Right? How can you then be fair in this concept, in this context? Well, being fair in this context is not that easy and depends on, there are many ways of defining fairness. But a very simple one is the following. You try to be proportionally fair. Proportionally to what? Proportionally to the channel capacity, the average channel capacity per user. What does it mean? As I said to you, you have a kind of round robin process. So you take one packet from the first queue, you transmit it. You take another packet from the second queue and you transmit it, and so on, right? This is what you do, right? In the end. The problem is that now, if the capacities are different, the transmission time will be different. If the rate is low, it takes more time to transmit. If the rate is high, it takes shorter time, right? Clear, everybody? So, in principle, you can have two possibilities. Perfectly fair. Perfectly fair means that you schedule one after the other, regardless of how long it takes to transmit. In that case, in the end, all the users will receive exactly the same average rate. This perfectly fair approach one after the other with different lengths in time, is not used very often, or very rarely used. What is used is the proportional pair, which means that the scheduler will work as follows. The time assigned to each user is fixed. Again, this is kind of an approximation of what is really done in practice, but let's see it like this. So the time is fixed, and the number of bits that you can put in a fixed time depends on the channel rate. So if the channel rate is high, in a given time you can transmit more bits. If the channel rate is low, then you can transmit fewer bits in the same time. Obvious, right? So it's kind of assigning to each queue, or each queue, a fixed container, and then depending on the channel quality, the specific connection, the specific flow, will be able to put a number of bits that depends, that is proportional to the capacity, right? So if you are fair in time, in practice, what will happen is that the average rate per queue will be proportional to the capacity. This is a very simple definition of proportional fairness. Fairness which is not absolute, but proportional to the channel quality, average channel quality. This is actually the most common approach that is used in mobile networks. The most common approach that is used in mobile networks. So in general, all these systems use an approach to scheduling which is more or less based on proportional fairness. Okay? This is done in these networks. Right? Very well. Now, given this, how can we characterize our packet transmissions, right? So of course, we could in principle characterize transmissions of single packets. But, you know, for an mobile radio network operator, it does not make much sense to characterize the behavior of the network for individual packets. What is much more interesting is characterizing specific transmissions of groups of packets. Okay? Because this group of packets typically are the application level units, the different applications running on our smartphones have to transfer in order to be able to provide some specific service to their end users. Right? So what we typically do is that we try to calculate the download or upload rate of application level messages, files, for example. If you make a download of a file, you make an upload of a file. This is what you do with your applications, right? How long does it take to download a single file? How long does it take to upload a single file, right? This is probably a much more relevant information which can characterize the quality of a network, rather than just the delay of a single packet, for example, right? So, let's assume that we want to calculate this time, the time for a download, again, or upload, but let's focus on the download because it's the most common one. How long does it take if you have a message of X bits, a file of X bits, how long does it take to download this file, D? This is the time that we want to calculate, right? And not only, we also want to calculate V, which is the average download rate, right? During the transfer, during the download, what was the average transmission rate? Okay? this is exactly what we want to calculate. So we have different channel rates, CI capacities, channel capacities. We have data transfers with X bits per unit per file. We want to calculate the delay of X, of transferring X, and the delay and the average rate of transmission V during the transfer. Okay? Probably you have already done this many times, right? How many of you have ever used speed test, Ookla speed test? Everyone, right? Well, this is exactly what you do when you test the quality of your network, right? You make a download of a file or upload of a file. You calculate the time it takes, and based on that, you calculate the rate. So you calculate D and you calculate V. This is what you do, right? This is done continuously in mobile networks. This is the main performance indicator that is used by mobile operators. This is even used by regulation authorities for making benchmarks between operators. So, for example, for sure in all European countries, but this is very common in also other countries, you have these official tests that are done in all the country by independent agents or companies that are assigned the task by the regulation authorities. They go around in the network and they make this kind of tests with fixed points for all operators. And they, of course, publish the result of the comparison. So in that point, in this room, I make a comparison between the 3-4 operators that I have, right? And can say, okay, the download rate for the operator A was VA, VB, VC, and then I publish the results. So that users can compare and decide if they want to make a subscription to operator A, B, C, or D. Okay, this is how it works. You may argue if this is actually really related to the quality perceived while you are using a smartphone. Is this really the only indicator that gives you the perception of quality, or good or bad quality? Well, of course, there are other elements that should be considered, right? But for sure, this is the main one. And also because of the popularity of this kind of tests that we make, typically when we see something that is not going well with our connection, right? Before complaining and making a call to the call center and complaining on the quality of our connection, we first make a test, a speed test, to say, I just made a speed test and the quality was very bad. I want my money back, right? They will never give you money back, but at least you can complain with the call center, right? Okay. So can we calculate this in the network? That's the point, right? Can we? Well, of course, we can measure it, but that's easy, right? The point is, can we calculate it based on the traffic model? So given the traffic that we have, can we calculate what would be a speed test in a given point of the network? This is what we want to do. Clear? Okay, good. So, let's consider the case of first case, simple case. All the capacities CI are equal, C. So the channel qualities are identical for all users. Okay? So if we have n active users, n active flows, right? The capacity C is simply divided by n, and we have a rate, instantaneous rate per flow, which is C divided by n. Okay? Obvious, right? Okay. Now, this is known as processor sharing model. So processor sharing model is a model where you, every time you have a new request, you activate a new server. but the service rate of the server is actually depending on the number of active servers. Okay? So if you have n flows, you have each server with capacity C divided by n. If you increase n, you, of course, decrease the capacity. If you decrease n, you increase the capacity per server. Okay? So it's a service model which is somehow similar to the models that we have studied, right? But with some different characteristics. Because you don't have a fixed number of servers, you have a variable number of servers. Okay? This is it. Actually, this model, which is apparently weird and different from the others, is very, very nice to be analyzed, because we don't really need to analyze it in the way we describe it. This is a model which is belonging to a class, very well-known class of Q models, which are known as symmetric Qs. And in case we have a description of the system using X, the number of bits, which is exponentially distributed. You remember, we used Markov chains, and in order to use Markov chains for modeling the service system, we need to assume that the arrival rate is a Poisson process, and also the service time is exponentially distributed, right? So let's assume that X is exponentially distributed. Well, in that case, this Q is completely equivalent, this Q, right? This fair sharing process, which is the one that I was depicting before. But this time, not with different capacities, fixed capacity C. So the capacity is fixed. So you have this perfectly fair division of the capacity. You divide the capacity exactly in n slices, and you use each one for a single flow, right? Which means that you are not really looking at each individual packet, but you are looking at the flow, right? Flow bits. Okay, so it's a flow model rather than a packet model. Well, if you assume that the queue is infinite, you don't have problems in storing information that must be transmitted. So you have your output queue that is infinite. Then you will serve all traffic, right? You will serve all traffic. This traffic that you serve is then following a mechanism of transmission which will simply follow the arrival process. So every time you have a new arrival, you just add a new server, and you start transmitting the bits of that specific request, right? So in statistical terms, the description of this queue is identical to the description of another queue, which is very different, but in terms of the channel occupancy is perfectly equivalent, because it's belonging to the same family of symmetric queues, and in particular it is equivalent to the MM1 queue. The MM1 queue is this one. Infinite queue, arrival process is lambda, single server, service rate is mu, which means that transmission time is 1 over mu. Okay? So arrival process, lambda, infinite queue, service time, service rate mu, which means that transmission time t is equal to 1 over mu. Okay? We assume that the service time actually is exponentially distributed. So again, we can write down a Markov chain, then the Markov chain is like this: 0, 1, 2, 3, and so on. We have lambda, we have lambda, lambda, and so on. And we have mu, mu, mu. Obvious, right? So how do we solve this Markov chain? You remember it's a Birkenbeck process, like the one that we have used for the RLP. So we just cut it in different points and we write the equations, right? So it's easy to see that we can write pi e equal to lambda divided by mu to I pi 0. Right? Because you start from this one, it's lambda over mu pi 0, then you have lambda over mu pi 1, which means lambda over mu to square pi 0, and so on, right? Very simple. This is the equation. So, how many packets do we have in this system? We know that the process that we write is nt, right? N over t is the number of packets that you have in this system over time, right? Can we calculate the average value of n? What's the problem?
What is n?
Hmm?
What is n?
This one?
N.
N is the average number of packets in the queue. So 0 packets, 1 packet, 2 packets, and so on. Okay, now we can solve the equations and calculate the vector of probabilities, and somehow we can use the information that pi I is proportional to the value lambda over mu to I, which is what we call rho to I. And basically, we can replace here the average value with rho to I. Again, this step is something that would require some more time, but we can calculate the average number of users like this. Now, this is a series that can be solved, and the final result of this series is rho divided 1 minus rho. Okay? This is a known series that can be solved, of course, assuming rho is less than 1, otherwise it doesn't converge. Okay? So rho must be less than 1, and that's obvious because the arrival rate must be lower than the departure rate. So this is what we have, right? So the average number of users in a M1Q is given by this expression, which is, again, directly coming from the simple Markov chain that we use here. Now, how can we use the average number of users? We know that if we consider this a single system here, we can calculate the time it takes for a request from arrival to departure, from entering here to getting out from here, right? And this is given by the Lichter result. The Lichter result is that the average number of users in the system is given by the arrival rate times the average time spent in the system. Let me call it yes, MT. So. To avoid confusion, let me change again the notation. Average time here. Okay? So if we want to calculate if we want to calculate this average time spent in the system, we can simply get the average value n divided by lambda, right? Right? Little result resolved by the average time here. It's average number of users divided by lambda. So we have the average number of users, we have to divide by lambda, right? So it's 1 over mu divided by 1 minus rho. Okay? This is our time, the time spent in the system. Rho is lambda over mu. If I divide by lambda, okay, I get 1 over mu. Clear? Clear for everybody? So the nice thing in this case is the following. Both the average, the distribution of the number of requests in the system, the average value here, and the average time spent in the system for the MM1Q are identical to the one of the processor sharing case. Are identical to the one of the processor sharing case. Which means that if we want to calculate this time, the time it takes for what? For our download of a file, the time, the formula for the time that we need to use is the same one that we have for the MM1Q. Why? The reason is simple. The reason is that since the workload that we have in the system is exactly the same, we don't lose any traffic, and the mechanism of transmission is the same, the internal process, the statistical process of the traffic management is identical in terms of the statistical description of the process, and in the end, on average, we get exactly the same value. Somehow it's kind of an extension of the balance equation that we need to use for the little result. So the processor sharing model is described the same equations like the MM1Q, even if, of course, this Q is very different from that one. But the time spent in the system by a request, on average, is the same. Okay? So our value D is then given by the transmission time divided by 1 minus rho. Transmission time divided by 1 minus rho. What is the transmission time? Transmission time is mx is the average file size divided by the capacity, this is time, in bit per second, right? Divided by 1 minus rho. The traffic rho is lambda, arrival rate of our traffic, times the number of bits per request, mx, divided by c. This is the average channel load. Clear? Okay? So this formula is the same formula here. We are just using the notation that we have defined for this special case. Mx is the average value of x, where x is the file size in bit. C is the capacity in bit per second, and rho is the total load on the channel, which is the total amount of bits arriving, so lambda times mx, which is the total arrival rate in bit per second divided by the capacity in bit per second. And of course, rho must be less than 1. Clear for everybody? Very good. Now, there is another interesting result, which is that the delay, the conditional delay, in the case of this Q, this is something that can be proved also for the MM1Q, right? But this result is valid not only on average, but also considering conditional probabilities. In particular, what is the delay, the average delay of a file given that the file size is small x? Okay? If I know the file size, it is x, like when I make the speed test, I know the file size. Okay? So given that I know the file size, what is the average download time? This is given by the same formula, where I replace the average value with the known value of the file size. Instead of using the average value mx, I replace it with x, which is a given known value. Same formula. How, of course, must be proved considering the conditional probabilities. Well, this is exactly what we were looking for, because now, what is the average rate during the download? The average rate during the download is simply given by the file size divided by d, by definition, right? Bits divided by time. So how was the transfer rate? File size divided by the time it took to download it, right? And in this case, it is 1 minus rho times C. Very nice, right? And this is clearly showing you that your download time, okay, is proportional to the residual capacity. Rho is the channel load. 1 minus rho is the residual capacity, normalized residual capacity, right? So your download rate is inversely proportional to the residual capacity. Okay? Clear? This is the reason why, of course, when there is traffic, and that's obvious also by the definition of process sharing. When there is a lot of traffic, you have a low rate. When there is little traffic, you have a rate which is, however, which is depending on the channel. Okay. So next time I will extend it to the case of different channel rates. You will see that it's fortunately we can simply prove that the same formula can be used also in the case we have different rates. It's a little bit tricky to explain why, but it's not that easy. Okay? See you after the break.